So, hello everyone, the recording has been commenced, and now we are going to discuss the seventh assignment, which was rolled out in the previous year. And I'll be taking your questions and I'll be interacting the same with you there. So, I hope you can see the screen. Uh, if you can see the screen, please respond in the text. So, Aman, can you see the screen? Aman, can you see the screen? Okay, that's great. Uh, So the first question is regarding the transient operation of a capacitance, right? So a capacitance is there and it's charged for a substantial period of time. And then it is saying that the capacitance is being disconnected from the independent power supply, right? And then it's asking you to find the voltage of the capacitance as a function of time. So, tell me if you have a capacitance, right? Voltage V. If you have a capacitance, what will be the steady state voltage of the capacitor? Aman, you can unmute yourself and answer. What will be the steady state voltage of the capacitor, Aman, in this case? If you have a voltage source, you have a resistance, you have a capacitance, what will be the steady state voltage of the capacitor? Okay, for some reason he's not able to answer. So let me just uh, so the voltage here is going to be given. Voltage here is going to be given as V is equals to voltage of the capacitor. V as a function of time is going to be given as voltage V, 1 minus e to the power minus t by RC, right? This is a very useful expression of the voltage across a capacitor when connected to a voltage source via some resistance. And I'll urge all of you to kind of remember it. It would be very useful if you are going to remember it, right? The derivation of the same was discussed in the previous interactive session. You can go through the previous interactive session to figure this particular thing out, right? How it was derived. And from this expression, it's very evident that if time t tends to infinity, then the voltage Vc as time tends to infinity will tend to voltage V, right? So this is something which you must kind of remember, and then the same thing was discussed in the previous interactive session also. So this implies that as the time goes to infinity, the capacitance acts as an open circuit, right? It will have the total voltage appearing up across it, and the current flow through it will diminish to zero, right? So the same logic can be applied here as well. So if the capacitance is, if you see in this particular circuit, if the capacitance is like open circuit, then what is the potential at this particular node, right? So let me call the potential at that particular node as voltage V, right? So then using KCL, I can write the nodal equation at this node, right, to be equal to 40 minus voltage V divided by 4 is equals to V divided by 10 plus V minus V by 4 divided by 5, right? if you are going to solve it, it will become it will give you voltage V is equals to 20, right? You solve it, you'll get voltage V is equals to 20, right? So that implies that the steady state voltage of the capacitor is equals to 20 volts, right? Now, if that is the case, and if you are opening the switch now, then the initial charge of the capacitor, right, will be corresponding to the voltage of 20 volts, right? So yeah, initially the capacitor will have a voltage of 20 volts, and then it will slowly discharge towards a more steady state, some other steady state voltage, right? So the circuit in the second half after time t is greater than 0, right? So this is for time t uh, less than 0, equal to 0. Voltage was of the capacitor was 20 volts. After time t is greater than equal to 0, what will be the state? So you can again write the KCL equation at this particular node, right? And then figure things out from there, right? So uh, I can write I can write that VC or voltage, this voltage is V, right? So voltage V divided by 4 minus voltage V divided by 5 is equals to V by 10, right? And this capacitance would be discharging, so it will be minus C dV by dt, and C is equals to 1 over here, so you can just write it as 1, right? And then you are left with this particular equation, right? So it's a differential equation, you can solve it, and then you can get the expression of VC, right? So how to solve it? So I can write it like this is 3 by 4 times of V. So just let me use the calculator now. So 3 by 4 divided by 5 minus zero point 0.1, right? Okay. So V by 20, correct, is equals to minus dV by dt, correct. And the rest is very easy. You can write it as uh, ln volts time t by 20 with a minus sign, and this will be going from voltage of 20 volts, right? And this will be going to voltage V. This will be going from time t is equals 0 to time t is equals to t, and you will be now getting it as uh, ln V by 20 is equals to t by 20, or you can write it as exponential time t by 20 with a minus sign is equals to voltage V, right? Okay, okay. Somewhere I did a mistake, because of which it is coming as 20. It is coming as 20. It should be 25 actually. Uh, okay, just let me check where I have done a calculation error. Okay, so this is not V by 20. This is actually uh, V by, एक minute, just give me a minute. 2, 5, 1 by 4. This should be 1 by 4, V by 4. So it's Just okay, okay. Okay, for time t greater than okay. Yeah, so I have done a mistake over here. So for time t greater than 0, you can write the current as nodal equation as current discharging into this particular circuit as I is equals to C dV by dt, right? And from this point on, you can write this voltage minus this voltage. So V minus V by 4, uh, V minus V by 4 divided by 5, and this voltage divided by this resistance. So this will be V divided by 10, right? So this expression would change slightly, right? So it will become, this will become plus over here, right? And this will become equal to with a minus sign because you are taking discharging potential of capacitance. So the capacitance would be discharging, right? So therefore it is minus C dV by dt, and the current is going into this particular node, right? So minus C dV by dt, the discharging current of the capacitance, is equals to the current flowing outwards, that is potential V minus V by 4 divided by 5 as is written over here, right? And plus V divided by 10. So plus V divided by 10. So this is going to give you V by 4 and is equals to minus dV by dt, and the remaining thing will remain the same. So this will be just V by 4, and the other things are going to remain the same. This will become, right, and this will be 20 times, right? So if you are going to do this, you are going to end up with this, right? So barring that minor calculation error, I hope everything else was evident to you, right? So, so what is the thing which you are learning from this particular question? The thing which you are learning from this question is that the capacitance, if it is connected to a voltage source for sufficiently long period of time, it charges to the same potential as that voltage source. So here, what was the voltage source? Voltage 40 volt, right? And you had all these network, resistance network. So what you did is you opened this particular capacitance and you figured out what is the potential across these two points, point A and point B, and whatever the potential was there, which came out to be 20, right? You fix that particular potential to be the initial state of the capacitance for the next time period. And then you wrote the KCL again at that particular point, and you solved it to get this particular equation. So this is how you have solved this is how you will solve question number 1. Is there any doubt in question number 1? Okay, if there is no doubt, let me just move forward now. So the next question is the initial charge in the 2 farad capacitor present in the circuit is shown to be 0. So the initial charge is 0. That means that initial potential is also equals to 0. So V initial is equals to 0, right? The energy in joules transferred from DC source until the steady state is reached, right? So what is the energy transferred? Energy transferred will be equal to the potential 12 volt, right, into I of t dt integral 0 to infinity, right? This will be the total charge which is, total energy which is transferred from the 12 volt battery, right? So how to figure this out? So if you have the expression of current, you can figure everything out, right? That's the simplest thing which you can do here, right? So how to figure out current? This is what? This is an RC circuit, right? With this resistance network present in the as a effective value of R. So what is the effective value of R which is connected to 2 farad capacitance? You can see that this is a Wheatstone bridge, so no current is going to flow in this particular resistance, right? So because this is a balanced network, so you can just eliminate this out. If you're eliminating this out, then these two, block A and block B, are coming in parallel, right? Wherein these elements are individually in series, right? So what you're going to do is that you are going to add them up, right? So this will become 8 ohms and this will become 8 ohms and 8 and 8 in parallel. So this will be implied this is equals to 4 ohms, right? Now, the capacitance, you have a capacitance, you have a resistance. What is the current flow? So, the current flow is going to be equal to I is equals to, what is the initial current going to be? What is the initial current going to be? How is the capacitance going to behave at time t is equals to 0? It's going to be a short, right? So at time t is equals to 0, the capacitance is going to behave as a short. At time t is equals to infinity, the capacitance is going to behave as an open circuit, right? So capacitance at time t is equals to 0 is a short. At time t is equals to infinity, it is an open circuit. So this is something which you must kind of remember, right? And similarly for an inductor, you can say at time t is equals to 0. For DC, it's open. At time t is equals to infinity, for a DC voltage, it's a short. This is for inductor, this is for a capacitance, right? So this is something which you must kind of remember. So here the current I is going to be given as V divided by R e to the power minus t by RC. How did I get it? I got it from the same expression which I've been using since the last lecture. So you write the KVL for this particular circuit, right? So what will it be? So it will be equal to, you can write that voltage V, and then I know that I is equals to C dV by dt, right? So it will be voltage V is equals to integral I dt divided by C plus IR, right? This is the KVL for this circuit, right? Now, what you can do is you have to figure out the current, right? So you can write it as a differential. So you take the differential, it will become 0 this side, and this will be I of t over C plus di by dt into R, right? And this is going to simply give it to give away as like uh, this will be di by I is equals to t by RC with a minus sign. This will become ln I t by RC, right? Integral from where to where? From V by R this is time t is equals to 0 and this is time t is equals to t. This is current IT, right? So this is nothing but V by R, and you can write from here that I is equals to e to the power minus t by RC V by R. V by R is equals to IT. So you got this expression from solving this KVL, right? And here what you utilize is that at time t is equals to 0, the current flow was equals to V by R, right? So current flow was equals to V by R because it's behaving like a short circuit, right? So this is an expression, again, this is an expression which you must remember. So in the first question, I told you to remember something like voltage of the capacitor as the final voltage 1 minus e to the power minus t by RC. And now I'm telling you to remember this particular equation. So these two are very important equation and you must remember them, right? Now going forward from this point, right, you have the expression of current uh, now with you, right? So you just plug in the values here now. So what's the value? Voltage is equals to 12 volt, resistance is equals to 4 ohm, right? E to the power minus T divided by RC. What is RC? RC is 4 into 2. So this is 8, right? So this is the expression of the current which will be flowing through the capacitance and hence via the 12 volt battery source. So what you do is you plug this particular expression in equation number 1, right? What is equation number 1? Expression of energy. And you integrate it, you will get the answer, right? So let me just plug it up. So 12 into 12 by 4 e to the power minus t by 8 dt integral, right? 0 to infinity. So this is what? This is 36 into 8. So if you are going to integrate it, it will become, this will become 36 and this will become e to the power minus t by 8, 0 to infinity, right? So this will going to give you 288 joules. So that is going to give you the answer number as C, right? And that is the answer, right? So I hope this question was clear to you all. If there is any question, please feel free to ask. If not, I'll move forward. Okay. Okay. I request you all to kindly mute your system. Ujjwal, I request you to mute your system. Okay. If there is no question in this particular part, then let me move forward. Uh, So question number 3 states in the circuit shown in the figure 3, the switch S stays in position A for a long time and reaches a steady state. Okay. At time t is equals to 0, the switch is moved to position B. Express current, derive the expression of current for all time t greater than 0. Right. So this is very similar to question number 1. Right. Except at time t is greater than 0, you are given an independent voltage source. Right. As opposed to the first case where you were given a dependent voltage source. That's the only difference between the question number 1 and question number 3 over here. So no big changes now. So if the switch is in position A for a long period of time, for time t less than 0, what is the potential of the capacitance at this point, right? What is the potential? So you can easily find it out because the capacitance will start behaving as an open circuit and it will have some fixed voltage across it, right? As was discussed in the previous question. So the potential will be equal to 3 divided by 3 plus 6 into 60 is equals to, this is 20 volts, right? So the potential will be equal to 20 volts, right? And this will be the initial voltage of the capacitance, right? Now what you're doing is that you are just turning this particular switch to position number B, right? So at position number B, what's going to happen is that you will do again the same thing. You will write the KCL at this particular point, right? So let me assume the potential at this particular node as a function of time to be voltage V, right? Therefore, the KCL at this point will be equal to 24 minus voltage V divided by 6, and this will be equal to, this is the incoming current, right? So the incoming current from this end, and the capacitor would be discharging. So the capacitor would be discharging, and totally it will be flowing in this particular part, right? So I can write voltage V divided by 3 and minus C dV by dt. So this is 2 dV by dt. So one thing which you must observe, guys, is that when the capacitor is discharging, right, I'm writing minus sign over here, right? So whenever the capacitor discharges, it's equals to minus C dV by dt. And whenever it is charging, it is equals to C plus C dV by dt, right? And it follows from the fundamental equation of Q is equals to C dV by dt. Q is equals to CV. So if you are going to take a derivative, it will become current I and C dV by dt. Here it is assumed that C is a constant, right? So therefore it can be taken out of the differential. What I have done is that I have taken a differential on both sides to give this, right? So here it was assumed that the capacitor was charging, therefore it is plus I is equals to C dV by dt. If it was discharging, then it will be minus C dV by dt, right? So since it is discharging at that particular point, it's minus C dV by dt. Now you might ask me a question, why did you consider it to be a discharging case in the first place, right? So, so initial voltage was 20 volt. You all agree with me that the capacitance is open. So the initial voltage is a simple resistance divider circuit. So it's 20 volt, right? Now the final voltage will be equal to, again, the same thing, right? The final voltage will be equal to 3 divided by 9 into 24 this time. So this is 3 and this is 8, right? So I see that the final voltage is lower than the initial voltage, and therefore the capacitor must have discharged, and hence I have written it as I is equals to minus C dV by dt. So now that we have understood how this equation 1 was derived, let's now solve this particular equation, right? So if you're going to solve this equation, it will become 4 dV by dt is equals to V minus 8, right? I just solved this question, solve this particular equation to get this final format, right? Now, if you are at this particular position, right, you can also write it as dV 8 minus 4V, and this will be minus T by 4 dt, right? And then you integrate it from both ends, from what? From 0 to time t, from what? From 20 to voltage V, right? And you integrate it, you will get it as voltage as V is equals to 8 plus 12 e to the power minus t by 4, right? Now this is the voltage of the capacitance as a function of time, right? What is the question asking you? The question is asking you to figure out the expression of current. Now, what's the current? Current is nothing but C dV by dt, right? So you have the expression of voltage, you multiply it with C, and you take the derivative of voltage. So if you take a derivative of this quantity and you multiply it by C, you will get the quantity as 6 e to the power minus t by 4, right? Now remember, this is the discharging current which we are seeing. So this is the current which would be flowing out of the capacitance. But what is the direction of the current which is given to you in the circuit? It's in this particular direction, right? So if the current which you have got is in the opposite direction of what the current has been displayed in the circuit, that implies that the current displayed in the circuit must be a negative of this quantity, right? Which you have got over here. So I of circuit is equals to I you have derived with a minus sign because it's just in the opposite direction. So that gives you minus 6 e to the power minus t by 4, right? So that is the option number D over here, and that becomes your final answer, right? So D is your final answer. So I am hoping that this question was also clear to you. If not, please ask questions here. If it's clear, I'll move forward. Okay, since there are no questions, I'm hoping that everything is clear here. Then in that case, let me move forward. So the next question is the switch shown in position 4 was in figure 4 was in position 1 for a long time and is moved to position 2 at time t is equals to 0. Determine the voltage for all time t greater than 0. So here what the question is showing is an inductor. So till now we have been dealing with capacitance, and now inductor has come, right? So how to address this particular problem, right? So as I had discussed with you in question number 2, that for a capacitance at time t is equals to 0, right? For uncharged capacitance, right? For time t at time t equals 0, if you are going to connect it to a DC source via some resistance, and this capacitor is uncharged, remember this, then it's going to behave as a short, right? And the current flowing will be equal to voltage by R, right? If there is some charge present on the capacitance because of which there is some initial voltage, then the current flow will be equal to V minus V initial divided by R. This you have to kind of remember, right? And at time t is equals to infinity, the capacitance will behave as an open circuit and the final voltage will be equal to the source potential across, it will be equal to the potential across the capacitance, with capacitance behaving as open circuit. So in this particular circuit, it's nothing but the source potential of V. So this is the thing which you must remember for capacitance. For inductor also I told you in the second question. So inductor, it will be, so initially there is no initial current flowing in an inductor, right? So inductor L, no initial current. And at time t is equals to 0, when it is connected via some resistance to a potential V, then the current will be equal to 0 at time t is equals to 0. That is, it behaves like an open circuit. And at time t is equals to infinity, the inductor will behave as a short circuit. So the current will be equal to V divided by R. Now you must kind of remember this particular two situations, right? And what if the inductor has some initial current, I0, some initial current is there, right? So what will happen in that particular situation? So in that particular situation, the same current will be flowing via that inductor at time t is equals to 0. So at time t is equals to 0, the inductor current will be equal to I0. Now, why did this happen? Let me kind of explain this particular thing for an inductor. Capacitance I have explained. Let me explain it for an inductor. So we know that the inductor expression is given as V is equals to L di by dt, right? So what is V? V is the potential across the inductor. What is I? The I is the current flowing through the inductor, right? And this expression of voltage and current is related by this differential equation. Now it's very evident from this case that if you want to change, bring about a change in di, a step change in di, right? So let's say I have I final minus I initial di, this is di, right? This is equal to di. And for dt, I have t final minus t initial is equals to dt, right? And this is equals to voltage V. Now if I final minus I initial is not equal to a small quantity, that is, it is the difference is substantial. However, the Tf minus Ti is equal to delta, that is, it's very small quantity, then this would imply that this expression is equals to infinity, right? Because a finite quantity is divided by an infinitesimally small quantity, that will result in infinity. Therefore, it implies that the current cannot change suddenly in an inductor. Remember this. This is a very important conclusion. The current in an inductor cannot change instantaneously. Okay, this is going back and forth. Instantaneously, right? So, therefore, what is going to happen is that if you have a inductor, as was there in this case, like if you have an inductor with some initial current flowing through it, let's say 2 ampere current, right? And the resistance here was, let's say, 5 ohm, and the 5 ohm, and the voltage was what's happening? And the voltage was, let's say, 15 ohm, right? 15 volts. So the final steady state current will be equal to 3 ampere, right? Because inductor will behave as a short, and the final current will be equal to 15 by 5. But then you must realize that time t is equals to 0, the current which will be flowing will be equal to 2 ampere. The current cannot change instantaneously, so it will be equal to 2 ampere. And if suppose there was no current in the circuit, if there was no initial current, then the there was no initial current in this inductor, then at time t is equals to 0, inductor would have behaved as an open circuit, and the current which would have flowed in this particular circuit would have been equal to 0. So this is the conclusion which can be drawn from this particular expression which is written over here, right? This is a very important expression. Now let's try to solve this particular question. So let me just copy it, keep it. Question number 4. Control C, Control V. Okay. So let me just try to solve this question now. So we have understood the working operation of an inductor. Now we can also write the initial current. So from the conclusions which we have drawn in the previous segment, we can write that for time t less than 0, since it is closed for a long time, inductor will behave as a short circuit, right? And the current which will be flowing in inductor will be given by so this is 24 volts, right? And the current is coming this way, so this will be equal to plus 3 I naught, and it reaches this particular point, so the potential at this point is equals to 4 I naught. So I naught is equals to 24. Okay, so I naught is equals to 24 amperes, and it's flowing in this direction. Okay, so the inductor current is also equals to 24 amperes, right? Because the same thing would be flowing here as well. Okay, good. Now what you are going to do is you are going to flip this particular switch to position number 2. Now if this switch is flipped to this position number 2, the current in this branch will be equal to 0. The current here will be equal to 0. I naught will be equal to 0 because this is an open circuit now. And since this is equals to 0, therefore the dependent voltage source, that is 4 into I naught, will be equal to 0. So this will be basically a short for all time greater than 0. A is shorted to B. A shorted B, right? Why? Because this 4 I naught becomes 0, right? Now, you know that the inductor is having an initial current of 24 amperes, right? Now, what is the current which will be flowing as a function of time for the inductor? So you have you have an inductor, you have a resistance, you have the initial value of current which is flowing through the inductor as 24 ampere, and it's very easy to solve now, right? Uh, Excuse me, like I think I have. Where is the sheet? Where is the sheet? Where did it go? Right. Uh, Here, just give me 1 minute. I think this I naught is equals to 24, uh, and the same current is going to flow via this particular the same. Just a minute. Just a minute. So the initial current of the inductor is not 24. I made a mistake over here. So I naught is the current which is flowing in this particular branch, right? And uh, this thing is connected like this at time t is equal to 0. But then there is also another current which can come from here, right? So the inductor current will be equal to sum of both these currents, right? Uh, so let me just try to correct myself. So I naught is equals to 24 over here. So the 4 I naught was equals to 24 into 4, right? 4 I naught is equals to 4 into 24. So the voltage across it was equal to 96 volts, right? Now we know that if the inductor is present in the circuit for a long time, it is going to behave as a short circuit. So the current flowing in this particular branch will be equal to 96 divided by 2. 96 divided by 2. And since the potential is positive like this and this, therefore the current must be flowing like this. So it will be equal to 96 divided by 2, that is equals to 48 ampere. So initial current present of the inductor is going to be 48. So my mistake over here, like, so the everything was correct except that I did not take the final voltage and divided by the final resistance. So now it's correct. So it's 48 ampere is equals to the initial value of the current of the inductor, right? Now you have the inductor L, you have a resistance R, and then you are required to find the expression of IT, right? How you are going to do that? So the inductor is going to discharge, right? So it's going to be a voltage V across the resistance is the voltage across the inductor, right? And what is the voltage across the resistance? It's equals to I into R, right? What is the voltage across the inductance? That is equals to L di by dt, right? And since the current would be discharging because it's now in a circuit with initial value of current, and the current will try to dissipate in the resistance, so it will be minus L di by dt, right? So you can again write the integral. So it will be equal to di divided by I, and this will be minus R into L, right? Sorry, R, not R by L, R divided by L, right? And minus sign because this minus sign is present, and di by I. And you will be integrating it with respect to dt. So if you are going to integrate it, it will be di by I integral dt integral L by R with a minus sign from time t is equals to 0 to time t is equals to t, and the current I is equals to I naught to current I is equals to I, where I naught is the initial current, right? So I'm deriving it from for a general case. So if you are going to solve it, it will become current I is equals to I naught e to the power minus t L by R. Now what is L by R? L by R is the time constant, right, for a LR circuit, right? And this is the expression of current which is flowing through a inductor as a function of time. Again, this is a very important expression and you guys must remember it, right? Just as the two expression in the capacitance, this is a very important expression for an inductor, right? So, once you have this particular expression, you can just plug in the values over here. So I of t will become 48 e to the power minus t. What is L? L is 0.5. And what is R? R is 2 ohms. 2 ohms, right? So this will become 48 e to the power minus 4t, right? Now this is the expression of current, right? And this is how it would be discharging, right? But what is the expression of voltage? This is what the question is asking. So for expression of voltage, what you are going to do is you are just going to take a derivative of it, and you are going to take a derivative. It will become V is equals to minus L di by dt, because it's discharging, right? So it's going to be 48 volt and e to the power minus 4t, and minus sign will be there because you had this, and then its derivative of this quantity is nothing but minus 4. So it will become, it's going to become, and of course L is also going to come. So L is 0.5, right? So L is 0.5. So you multiply 4 into 48 into 0.5, you will get 96, and minus minus will become plus. This is 4t, right? So this is the expression which you will get, which is expression number B, and this is your final answer. So I'm hoping that this is also clear to you. If not, please ask question, and if there is some, I'll address those. Okay, so I'm hoping this question was also clear to you. If there is any pending thing, which if there is any question which you have in days to come, please feel free to ask. I'll address them in the next lecture as well. So no big deal there. Okay, question number 5. So the question number 5. So it's asked that the circuit, the toggle switch, this is a kind of a single pole double throw, right? So this is single pole double throw. So this is something which you will learn in your machines course as well. What is SPST, what is DPDT. So this is just the extra information which I am giving you here. This is a single pole double throw kind of a switch. So these are the throws over here. This is a single pole. So it is connected to position number 1 here for some time, right? And because of which the capacitance is going to be charged to 10 volts, right? And once it is flipped to position number 2, this capacitance will discharge into this particular capacitance of 4 volt, and together they will have some expression of voltage, right, as a function of time. Now the question asks you to figure out what is the potential of the second capacitance as a function of time. This is what the question is asking you, right? Now even if you don't rigorously solve it, right, from the 4 expression of voltages which is given to you, you can figure out what is the correct answer. Let me show you to you how, right? So this is going to save some time in competitive examinations if you are planning to write it, right? So how are you going to solve it? So you are having a 10 volts over here, right? And it's connected to position number 1. So the final voltage, so the initial voltage will be equal to 10 volt. Very obvious, right? And it's also evident to you that like this 10 volts would be discharging into this particular capacitance, and the final voltage of this capacitance has to be equal to 0, because the energy which is coming to this capacitance is coming from this capacitance. However, there is a resistance in between, so all the energy is going to dissipate, so the final voltage has to be equal to 0. So if you look at these four solutions which is given to you, options which is given to you, you see that at time t is equals to infinity, the potential for part C and part D do not turn up to be 0. They don't turn up to be 0. V is not equal to 0 at time t is equals to infinity. Therefore, option number C and D is wrong, right? Straight away. How about option number B? Option number B is saying that the voltage is equals to 10 volts at time t is equals to infinity. At time t is equals to 0, the voltage is equals to, time t is equals to infinity. At time t is equals to infinity, the voltage was equal to 10 volts, right? So this can also not be the case, right? This can also not be the case over here, right? So the only option which is remaining with you is option number A, right? So, and that is the correct answer. So how to address it in a more rigorous manner, right? So let me try to solve this particular question for you guys, right? Uh, and then you can figure things out from there, right? Uh, so uh, so uh, the potential at this particular capacitance at time t is equals to 0, greater than equals to 0. The potential is equals to 10 volts, right? And the same would be dissipating in this particular capacitance. So I can write that the current here is going to be the same, right? So I can write that V1 minus V2 divided by 2, V1 minus V2 divided by 2 is equals to C2 V2 by dt. Now what is V1? V1 is the potential at this node, right? What is V2? V2 is the potential at this node, right? And I can also write that C2 dV2 by dt is equals to minus C1 dV1 by dt, right? Why this situation? Because the current is equals to same, because they both are connected in series, and one is charging, one is discharging, so I can write this, right? Now if I'll take an integral of both sides, right, and integrate, it will become C2 V2 is equals to minus C1 V1 minus 10. Why did this happen? Because the initial voltage here was equals to 10 and the final voltage is V1, and the initial voltage was 0 and the final voltage is V2. So from here you can write this particular expression, right? Now if you have this particular expression with you, and if you have this expression with you, right, you can substitute this equation in this one to figure things, to make things easier, and then this will become the equation number 1 will be a equation in a single variable, differential equation in a single variable, which is like solvable, right? So you are left with minus 3 V2 plus 10 divided by 2, right? Now if you have this expression with you, like we have solved numerous times, right, such kind of expression. So this is nothing but minus 3 V2 plus 10 divided by 8 times of dt and 0 to time t, and this is 0 to voltage V. So you will get V2 as 10 by 3 1 power e to the power minus t divided by 3 by 8, right? So this is the expression which is resulting into expression number A, and that's the answer to this question. So if there is any doubts over here, please feel free to ask. If there are none, I'll request you to join the next live lecture series by my colleague, and we can wind up this particular session. So I'm guessing that there are no doubts here. So let me stop the recording.